All right, so they're not necessarily going to go through all of them, but at least want to hit a couple of them. I might do them all. All right, so first off, what's Newton's first law of motion?
Something about inertia, right?
Yep, it's all about inertia.
Things in movement want to stay in movement. Things in motion want to stay in motion.
Is there a difference between those two?
Did I say movement the first time?
Yeah.
Things that aren't moving want to stay. Things that are, not moving.
Yeah, okay. Things that want to keep doing whatever they're doing. Thus the inertial growth story. So, in this particular case, I have 3 pucks traveling on horizontal frictionless ice at different speeds, which requires the most force to keep it sliding.
It's all equal. It's all equal. Isn't
Yeah.
it?
Because none of them require anything to keep doing what they're doing. Second one's a Newton's third law. Man pushes down on the ground with a normal force of 133 megadynes. That's just the unit of force. So the Newton's third law is you just flip the 2 objects and switch the direction, and everything else is the same. So if the man pushes down on the ground, then the ground pushes up on the man, and then the rest of it with the normal force of 133 megadynes is the same.
Did you say number 1 was Newton's first or second?
First, well, I mean, Newton's first is just the wordy version of Newton's second. But typically the first one is associated with Newton's first law. Second one, problem 2, is associated with Newton's third law. And Newton's second law just shows up in a whole bunch of other places. All right, so in problem 3, we've got this should work. Mass 1, mass 2. So you're pushing up on this as the book slides down, I believe. Let's see, box 1. Mass 2 is slipping down the wall, mass 1 is moving up relative to mass 2, down relative to the wall. So this is the basic scenario here. Like that. And the question is, which way is friction acting on this object? No. Friction is not perpendicular to the surfaces. Pardon?
We're talking about mass 1.
Yes.
So it would be friction would be down
And why would friction be down?
because it wants to move up relative to what it's touching.
Yes. It's irrelevant about the wall because it's not touching the wall. There's no friction between mass 1 and the wall. Now friction on mass 2 would be up from the wall. And it would be up from mass 1 as well.
So wait, is it going down or up? I'm confused.
The friction on mass 1 is going down.
But on 2, it's going up.
Yes. Because mass 1 is going up relative to what it is touching, and friction opposes that.
So on either side of the book, and in this, would friction be moving upwards?
Yes. Yeah. The wall and mass 1 are both exerting force upwards, friction force upwards. All right, so number 4, there are a couple key things in here. One, I gave you the force diagram, but the last sentence in the description of the box is moving at a constant velocity to the right. What does that tell you?
That it's in equilibrium.
Yes. And what are three manifestations of equilibrium? Yep, there's one.
Velocity is constant, and acceleration is 0.
Yep, there you go. Those are the three.
So is net force and what?
Say it again.
Net force is 0. Velocity is constant, acceleration is 0.
If any one of those is true, the other two have to be true. And I have four forces acting on it. I've got a friction force acting this way. I've got some external force acting that way. I've got weight acting down and normal force acting down.
It says it's tension.
Pardon?
It
Oh, did I say tension? Okay. So, I know the sum of the forces is 0. And when I add forces, well, I don't know the actual size of these, but I do have some sense of when I add them together, it's 0. So friction's going this way, that's my friction. And then normal force. And then tension and weight. I have to end up back where I started. And so just based upon this drawing right here, the directions have to be similar, have to be the same direction as in the drawing here. But normal force and weight are both vertical. Friction is horizontal and tension's at that angle there. So just based purely upon that, what's the size relationship between normal force and weight?
Identical.
What? Sorry, I heard two things at once.
They're identical.
Those look the same?
Or they should be identical.
Sorry, the upward pull needs to be counted by the tension. So they're not.
Are you saying there's something wrong with my drawing?
No.
It's terrible.
All right, so the upward pull,
So if you add the upward pull of the tension and the normal force and subtract away, it would be 0.
if you add,
Or rather, Ft sine of theta.
okay. So recognize the total force upwards is the normal force plus the vertical component of the tension.
And that's what I was trying to get to.
Okay. Chloe, you had your hand up.
I was gonna say what you just said.
Okay. So I know that this has two components here. This is, if that angle there is theta, this becomes Ft sine theta, Ft cosine theta. So which is bigger, normal force or weight? Yeah, so I know weight is bigger than normal force. What about tension and friction?
Friction is equal to Ft cos theta.
Okay, so therefore,
Therefore, I don't know. What do you mean by therefore?
which one's bigger, tension or friction?
Tension?
Yeah, just looking at the drawing here, this has to be bigger than that, because that distance right there is friction. That's the hypotenuse is gonna be bigger, so my tension is bigger than the friction. And I forget which choice that was. That was B is the answer. Now, if we wanted to do it more analytically, we look at the equations of motion. I have Ft cosine theta minus the friction, which is my horizontals, is equal to 0, because we've established acceleration is 0. And then we have Ft sine theta plus y minus the weight is equal to 0. So manipulating this equation right here, I have that the y is equal to weight minus Ft sine theta. assuming ft sine theta is not 0, which yeah, I'd do another version of this problem in a different test where I explicitly state that theta is in between 0 and 90 degrees. But the normal force is the weight minus something, therefore the weight has to be bigger than the normal force. Or from this one right here, I have the tension cosine theta got to be equal to the friction, or the tension is the friction divided by cosine of theta. And since cosine of theta, assuming theta is not 0 degrees, cosine of theta is less than 1. Therefore, the tension is equal to friction divided by some number less than 1. Therefore, the tension is bigger than the friction. So analytically, you got that approach, and then graphically, you got that approach. Questions to hear about any of the first 4 problems?
So, those equations that you just did are the equations of motion for the box?
Yes.
So, underneath explanation for B, what would that be? Is that not the same thing?
Your explanation could be the sum of the forces adds that up to 0, and then I have a trapezoid here. This is clearly longer than this side. This is clearly longer than that side. Or mathematically, you got the equations of motion that you can set it up like this, or even just solve for weight. Weight is the normal force plus Ft sine theta. So the weight is the normal force plus some number, so weight has to be bigger than the normal force.
Can you repeat the last thing you just said?
If we solve for weight instead of solving for normal force, we have weight is normal force plus something. So the weight is the normal force plus some number, therefore the weight has to be bigger than the normal force. And although it's implied in the problem, I didn't state it explicitly, theta is between 0 degrees and 90 degrees.
I have a question.
Yep.
So why does tension equaling friction divided by cosine mean tension is more? Because what if cosine of theta equaled like 0.7 and tension was 4 and friction was 3? That would make friction actually.
The tension would be greater than the friction in the scenario you just gave me.
Yeah. Yeah, I found where I was confused.
Now, if we actually went with the numbers that you just said, I think you said this was 4, this was 3, and this was 0.7. It doesn't quite work out the equal, so
Yeah.
therefore it's actually not an equilibrium if that's the case. Other questions? All right, so now we get into a slightly more interesting problem. So we're dealing with a centripetal motion problem here. It's somewhat similar to the lab. I mentioned that the hammer is being whirled around horizontally at a constant speed. Those are some big clues. And so as we're watching from the side, basically we start out with force diagram. What are the forces acting on the ball? Or the mass?
Weight down.
Force of tension up to the left.
That angle there is there. else?
No.
All right. What is the direction of acceleration?
To the left.
Yep. Acceleration is that way. Because again, it's traveling in a horizontal circle, I know the acceleration is towards the center of it, and horizontal, well, the acceleration is horizontal. So we're gonna need to break up the tension here to figure out how much, wrong one. How much is to the left and how much is upwards. So I know the upward one, that's going to be the opposite side, so that's Ft sine theta. And then inwards, Ft cosine theta. And the weight's acting down.
Are you writing this?
Pardon?
backwards? Are you writing this backwards?
I don't think so. What do you think is backwards?
Like, the theta sign was on the other side.
Oh,
Does it have like?
the theta that I give you is this angle right here.
Yes.
In essence, those two angles would be congruent. So if this angle with
Oh,
the
okay.
horizontal is theta, then that angle there is
Oh,
theta as well.
Thank you.
Okay.
I forget what law that is, isn't it law of congruent angles or something?
Two parallel lines cut by transverse alternate interior angles are congruent.
Okay.
I don't know if there's a shorthand name for that. I haven't done geometry in a few decades. All right, equations of motion. Because I think, so part A was force diagram, done. Yeah, draw the force diagram. Now, let's see, yeah, I mean, this would be acceptable for the force diagram, but you'll ultimately need to get it in that form. So what are the equations of motion?
Ft sine theta minus weight equals 0.
All right,
Ft cos of theta equals ma.
do some substitution here. So I've got, well, the formula for weight, which at this point, all of you know. And then Ft cosine theta is equal to m. Now we have two different formulas to choose for centripetal acceleration. We have v squared over r or omega squared r. In part B, I want it in terms of v. So v squared over r. And the question is, what is r? In terms of, and I can't tell you, let's see, I know that this length here, from here to here, is L. And the allowable variables are M, L, theta, G, and V. So M, L, got already.
Theta, G, and V.
Okay, thank you. And then I say any number, so I mean, if there's a 1/2 that needs to show up there, 1/2 does. These are the variables though.
So are we on B or C?
B.
Okay.
What is the formula for R in terms of one or more of those variables?
R equals mv squared divided by tension times cosine of theta.
Tension's not an allowed variable.
L cos theta?
Yeah, it's a lot simpler than that. This is basically, R is this distance here. this thing's traveling in a horizontal circle, the center of the circle is just below the fulcrum, where the top point. I got a physical triangle here of the hypotenuse is L, and I want the horizontal part of it, so it's just L cosine theta. And then part C is what are the equations of motion in terms of some or all of those quantities.
Dr. Fox, I'm confused as to how the ML theta GB plays a part.
Oh, the problem says that I want a formula for R using those variables. I don't want you using other variables other than from that list. That's the point of it. I try to limit the number of correct answers that there might be.
So you're saying I could do N cosine theta or G cosine theta, or is it a specific one?
Well, I mean, you're not completely making up what it could be, but based upon the problem, the fact that R is equal to L cosine theta, I mean, L and theta are on the list, I'm good with that. I don't want you to come up with a formula for R which has tension in it, because on that problem, tension is not an allowed.
So these don't represent something specific is what I'm getting to.
That M represents the mass of what's hanging at the end of the chain. L is the length from here to here. Theta is this angle. G, acceleration due to gravity, and V is the speed at which this thing is moving.
Okay, thank you.
Ah, okay. Other questions? All right, part C, what are the equations of motion? And we do throw tension into it, so basically those are the equations of motion right there. This would not be an acceptable final answer for part C because centripetal acceleration is not allowed and weight is not allowed. So I had to do it in terms of get past the substitution phase.
Would you need to put L cosine theta in the denominator since R is not allowed?
Oh, that's right. I don't have R in that list, so yes.